So continuing with the top quarks, so Luca will tell us about quantum SMEFT tomography with the top pair production at the LHC.
Okay, thank you to the organizer for inviting me. I'm really happy to be here and to talk about some work we have been doing with Rafa, Eric, and Fabio. So I'm going to take advantage of all the nice talks that happened before me, including the one just now by Dorival that gave a very nice introduction, to skip my introduction. But I'm going to just skim through it, okay? So we all know why we are here. We like this idea of bringing some quantum information studies and approaches to particle physics and to collider phenomenology in particular. And we are exploring why we are talking mostly about top quarks and electroweak boson is because they allow for the reconstruction of the spin through the decay, okay? As we are saying, the W is its own polarizer. The top has the lepton that decays in a correlated way. And then the Z boson actually is more complicated, but it's still doable. And in general, it can be shown that the spin can be reconstructed if there is some asymmetry between the left and the right-handed coupling. So we are mostly talking about bipartite systems. And the usual definition of entanglement is that the state is entangled if it's not separable. And in the more generic definition, we have that if we have a density matrix describing our system, it is entangled if it cannot be written as a product of two density matrices. Now, the fundamental object that we study is the spin density matrix that, according to the spin of the particle, will have a different dimension. It can be decomposed in general in the generalized Gell-Mann matrix. And when you have two particles, this is the generic expression, okay? And all of these parameters completely characterize the quantum spin of the system. Okay, so how do we build this density matrix? We do collider physics. We are very used to compute scattering amplitudes, and that's exactly the way we compute it. We define the R matrix, which is this matrix that describes the production of the particles in the final state, where you basically average over the initial state. And contrary to what you usually do when you do cross-sections, you don't just square the LHC amplitudes and sum them, but you also multiply off diagonal elements. And in doing so, you obtain a matrix, okay? And then this matrix can be decomposed in with the generalized Gell-Mann matrices, and we end up finding basically an unnormalized version of the density matrix. And once we take the trace of the R matrix, we recover our density matrix and we can do our studies. So in the particular case of the top pair, we have spin 1/2. So the Gell-Mann matrices are the Pauli matrices. And the first term here, this A tilde, is basically describing the differential cross-section, the usual differential cross-section we deal with when we count events. Then we have the degree of top and anti-top polarization, and if the interactions are CP invariant and P invariant, they are 0. And finally, this object here is characterizing the spin correlations. We normalize it, and we obtain a density matrix, okay? Now, as we are talking about, with this object, then we can construct various observables. One of them is the concurrence, okay? We can talk about the purity of the system, and finally, we can even talk about the Bell inequality through the CH-SH observable. Okay, so as Dorival said before, top pairs are an ideal probe because these spin correlations are preserved after the decay, since it decays before hadronizing. And so we can go on and compute this object for our experiment. And at the leading order in QCD, there are two main channels. There are two channels, the gluon fusion one and the QQ bar channel. We collide protons, so we get a mixture of these two channels. And therefore, our matrix is going to be a weighted sum of the individual R matrices of the partonic channels, and this weight comes from the parton luminosity, okay? So for the PDFs that describe the parton content of the proton. Now, a bunch of definitions just so that we're all on the same page. The calculations that I will present later on are done with usual helicity basis. When we talk about beta, we are talking about the velocity of the top quark, and cos theta is the polar angle with respect to the beam. We can define entanglement by means of this quantity here, delta, which is a marker that if it's bigger than 0, is telling us that the density matrix is describing an entangled quantum state. And then the concurrence is defined as the maximum of the delta and 0. And if it's equal to 1, we have maximal entanglement, okay? So what is the picture in the standard model? As we have seen also in previous talks, and here it's broken down into also the partonic channels. So we have the proton-proton, the total, the weighted sum, and then the individual partonic channels. We have a region that is not entangled, that is basically coming from the gluon fusion process. And then, and it's also present in the proton-proton case. Then we have maximal entanglement. We have maximal entanglement at threshold in a glue-glue, and also at very high PT and energy. And then we have also maximal entanglement in the same region in QQ bar, while we do not have entanglement at threshold for that case. And this is why, in the end, in the proton-proton case, we end up having maximal entanglement at high energy, but not at threshold, but still it's quite high. If we actually start looking into the precise form of the density matrix in the two regimes, we find that at threshold, for example, in gluon fusion, we have that the state of the top pair is described by a singlet, and in the high energy is described instead by a triplet, okay, both for QQ bar and for glue-glue. Okay, I'm going to start talking about a slightly different topic to introduce the SMEFT, because this was the picture in the standard model. However, many of us are interested also in looking for new physics, and there are two main ways to look for new physics. The first one is direct searches. We perform an experiment, we find a bump in the data, and we claim this is new physics, this is a new particle that we have discovered. There is a second way, which is through indirect searches, and entails scouting the tails of the distributions, because the idea is that this new particle is too heavy to be produced at the energy of the experiment, but it's close enough to start having some effect on the observables that we measure. And in particular, hopefully we can distinguish this green curve from the red curve. Notice that it's very important to distinguish these two curves to have precise predictions for the standard model. Otherwise, there is no way that you can distinguish the two curves. While this would not be the case if we are dealing with direct searches where bumps are more difficult to miss. Okay, so this is the situation we want to look at in particular, and so we need a framework to describe precision physics and heavy new physics, and one such framework is the standard model effective field theory, or SMEFT in short. Okay, so with the SMEFT, what we do is, okay, we don't want to add any new particle to the Lagrangian and to our model, but we want to add the new interactions. So the way it works is that, imagine there is some new particle, okay, eta, but we do not, which is mediating some standard model interaction, the interaction between standard model particles. The propagator is the usual propagator, and if we do not have energies close enough to reach the mass of the new particle, what happens is that, and actually if it's much smaller, what happens is that this diagram can be described by this sort of contact interaction. So by doing this exercise, one can see that if you are at energies much lower than the mass of the new states, you can describe the effects of this, of the presence of this particle without having it in your theory, just by having some correction to your scattering amplitude. So this leads us to build a new framework, which is the framework of an effective field theory. So if we do this exercise for the standard model, we end up building the standard model EFT, where we just build all of the possible operators, and we do so by preserving all the symmetries. Okay, this is just a bunch of an example of operators, which then enter and modify our scattering amplitudes. So this framework is the SMEFT, okay, as I said, where the standard model Lagrangian is extended by a tower of higher dimensional operators, which are suppressed by the scale of new physics. All of these operators are, for example, the ones shown before, and this framework is so-called, is said to be rather model independent because it maps to, it can be mapped to a large class of BSM models. The EFT to-do list usually, the EFT to-do list is a sort of list of things that we usually do in searches for new interactions. The first one is we define some target operators, because as you said, you've seen before, there are so many, and you sort of need to limit your scope. You want to find some optimal observables to probe them, and this is going to be the focus of this talk. And then you want to compute precise theoretical predictions and make accurate measurements. Okay. Allow me a quantum fluctuation to another field of research that is dear to me, and you can read about it in these two papers here, because it's really important when we talk about precision physics that we have theoretical assumptions under control. Okay. And often there are things that are overlooked. For example, we tend to use PDFs that have been fitted with standard model assumptions to do searches for new physics. This is clearly not theoretically consistent and can actually lead to some wrong results. Okay, go back to the problem of top pairs in the SMEFT and density matrices. We have what happens to the R matrix in the SMEFT. Again, the R matrix is the cross product of the LHC amplitudes. Now the LHC amplitude is going to be corrected by higher dimensional operators, and therefore we're going to have corrections to the density matrix. This is an example of the coefficients that we computed for analytically for different operators in different channels. And what I want to stress, okay, this is not TT bar, but generically this holds for new physics and different processes. The density matrix can open a window to new sensitivities. Okay, why? In this particular process, for example, the standard model is contributing to these LHC amplitudes, okay? And then the EFT is instead contributing to these other LHC amplitudes. So when we compute the cross-section, there is no interference. And the sensitivity comes from the square of the EFT. However, when we build the density matrix, we construct also the off-diagonal term. And therefore, we recover the sensitivity that otherwise was lost when we were looking at the differential cross-section. Okay? Okay, so now just some results from our study in the TT bar. This was a standard model picture. And this is, for example, the picture, how the picture looks when you induce some new physics. Okay, this is a specific operator. The effects are very mild and difficult to see from here, but what you can observe, for example, here is the quadratic piece is lowering the entanglement even in the high energy regime, and this can actually be seen a bit better if we look at the specific relative changes. Okay, this is the effect. You can see here that the quadratic term is lowering the entanglement here at high energy, and then effects are mostly relevant in the boundary regions, okay? Both for the linear case and the quadratic one. This was the case in looking at the whole phase space, okay, as a function of two variables. However, it's a bit easier to look at the average concurrence over the angular distribution. And if we do so, looking at this operator, both for PP and GG partonic channel, we can see the effects of having new physics producing this operator in the expected concurrence as a function of the invariant mass or of the velocity of the top quark. So the black line is a standard model. Okay, so we have entangled state closer to threshold, as this we know, and then we lose it. Once we add new physics, as you can see, it's quite interesting to notice that if you look at the partonic channel, the effects at threshold are very mild. Okay. In particular, we see that the linear corrections are from the EFT are basically non-existent. They vanish when you are at threshold. However, you have some effects from the quadratic corrections. We will see this better in a moment. However, you can have much bigger effects in proton-proton collisions simply because this operator is not only inducing new helicity states that then change the density matrix, but it's also changing the balance of the two channels with each other. So you might have more gluons than quarks and so on. Okay. Okay, so another thing we looked at was the quantum state, and in particular, what are the effects, the explicit effects of the new physics operators, of the SMEFT operators on the quantum state. So as I remind you, at threshold, we had that the quantum state in the standard model is a singlet. What happens is that these operators induce a triplet even at threshold, okay? So you start having a mixed state. And as you can see, the probability of having a triplet is proportional to this quadratic piece, okay? So it's only a purely quadratic effect. In the QQ bar, we had that at threshold, the state was separable, and it was in a mixed state of up-up and down-down combinations, where the mixed state was perfectly specular. So you had 50% probability of being up-up, 50% probability of being down-down, and the new physics effects are going to change this balance, but they are not going to change the nature of the state, which remains separable and not entangled. Okay, you are just going to change this probability. Now, why all of this is interesting in terms of new physics? It's interesting because you can break the generacies in the space of Wilson coefficients of the SMEFT operators. As you can see in these plots, where you have in these lines in black and the red one, which is the standard model-like, you have ISO contours of the cross-section. Okay, in a specific phase space point, which is a threshold. And then instead, if you look at these quantum observables, okay, here we plotted these specific probabilities, but you can do a similar job with concurrence and other observables. They probe different directions in the parameter space, okay? And so by adding these observables, one can hope to gain more sensitivity to new physics. Okay, this brings me to my conclusions. I talked about exploiting quantum observables specifically for new physics, and we know that in the standard model, these top pairs are maximally entangled at threshold and at very high energy, and that the SMEFT operators can induce the presence of different quantum state, de facto changing this balance and possibly decreasing the entanglement at threshold and modifying the overall pattern. Finally, I showed you that these quantum observables can probe complementary directions to the cross-section in the EFT parameter space, and therefore they can be very helpful in searches for new physics. Thank you.
Thank you very much, Luca. Questions?
A provocative question. The D observable measured by Atlas, minus 1/3 and so on. So at the end is built upon the C matrix elements, no? And how the EFT effect should,
So
I would say, that's actually the problem.
So you're one, yeah. So what we show here is that, okay, this would be in a way the plot to look at. You can go both up and down because it depends on the value of the Wilson coefficient. However, this effect is there because of not because of this, okay, which is very mild. So these heavy EFTs, these EFT operators, they affect the partonic channel very little, okay, because we are at threshold, so these operators tend to be important when you are at higher energies and so on. But they change a lot the balance between the two channels. So this effect you would see in a differential cross-section. You would have already seen it. So I think if you put together all this information coming from the differential cross-section, this would start to shrink a lot. And I don't know if you can explain a very large deviation.
This is integrated, right?
This is
from
integrated.
threshold to some beta value.
This is no, I think it's not integrated. So it's not. It's this quantity here. So you take the R matrix and you integrate the angle, and then you have it as a function only of S. It's not integrated until.
Okay.
To follow up, I mean, you don't have to just explain a deviation such as the one they have. You need to explain a deviation that decreases with energy in the Atlas measurement.
Yeah.
Because they are fine at 500 or more.
Yeah,
So
yeah, of course, yes.
It's
yes.
not.
Yes,
It's never going to work.
Yeah, it's difficult. Yes, I agree.
Still here?
Thanks. So nice. I have a maybe naive question. So, what do you do in order to define the optimal observable for each of the EFT operators you want to test? So, do you use something that is already there, so some observables that are defined because of some properties that we discussed in these days, or do you have some kind of optimization where you isolate an operator? I mean, you choose one operator and then you take the spin density matrix and try to really have an algorithm that selects what is a custom observable that is the optimized for that operator.
So no, we haven't done that, but it's actually, I mean, it's one of the points of that I wanted to stress in the talk, that once you study, yes, as you were saying, if you look operator by operator, you can start then, for example, I mean, this was, electron to WW, but leptons, yeah, E plus E minus to WW. But yes, imagine you compile a table like this, operator by operator, and then you start looking which elements of the density matrix are ideal for you, and then you devise an observable according to that. No, here we didn't do that. That was not the objective. We wanted to see the effects on the concurrence mostly, and that's what we studied. That's pretty much it. We didn't do any optimization.
Okay, thanks.
Any more questions? So I think some of the questions that were asked will be covered in the next talk. So we can thank Luca again